introduce from Feliks Przytycki, who will talk about not many periodic orbits in bunches per iteration of complex quadratic polynomials of one variable.
Morning, everybody. I must admit from the beginning it has three parts, which is listed top. One Cremer periodic, I'm not 100% sure. I'm sure it is correct, but the proof is not perfect in the version of arXiv. Okay, sorry it is written a lot here, but it is nothing special. I will discuss. No, it is abstract, so you can just read.
Okay.
I have to read, excuse myself, why it is so complicated on the first page. That's abstract, which I sent you out. So it has, as I told you, it has three parts, this talk. The first part is what happens close to Cremer fixed point. The second part is what happens along Cremer periodic orbit. I think this square is not needed here. It is in the version arXiv, but version arXiv is still has gaps. So I think I can improve the simple. And then point 3 is what I really want to achieve. That if we have a bunch of periodic orbits of period n, which go close to each other, so fjx minus fj is less than x minus delta n, where n is period, then there are not too many of them. There are at most exponential of delta n, where delta is arbitrarily small. So I conclude, due to my, this is my paper with Juan Rivera and Smirnov in ergodic theory and dynamical systems in 2004. It solves the problem of pressure. The pressure can be calculated in periodic orbits. I will tell you more precise. It was an open problem since the beginning of 2000s. The first paper on this was by Ilya Binder, Makarov and S. Smirnov, where we proved this, but assuming all periodic orbits to be hyperbolic. So I believe I proved that.
In part 3, those are different deltas. So the bound on the
It doesn't matter. It doesn't matter if you take different deltas, then you can decrease them to the same delta.
Ah, okay.
Intuitively they are different, but don't have nothing to do with each other. And here there are basic definitions. I will basically consider quadratic polynomial. Everything is correct for quadratic polynomial is correct for unicritical polynomial. Is in the power d. Yes. I asked Gennady about arbitrary polynomials, and as I expected, he concluded that this might be difficult.
But what?
The old theory. So to start with basic definitions, it is talk about pressure, so here is definition of variation of pressure. Variation of principle. And here phi is any continuous function in the space is compact. It's written. No, phi can be definition can be written for any continuous function phi, but I will concentrate on such phi equal minus t log f prime.
But then it doesn't have to be continuous.
No, it is not continuous, but the theorem goes through, and this was my topic of my research for many years. The basic observation due to which it makes sense is that this logarithm of prime is integrable. And even logarithm of prime is non-negative. Always, for every measure. So the variational principle is phi makes sense. So I proved it many years ago. It is published in Proceedings of Units. But later Juan Rivera gave half a page proof, which is unfortunately arXiv preprint never 20 years ago.
So a proof of what?
Integrability of this geometric potential. So don't read my check it out. Other pressures is tree pressure, where you take a good point. X, of course, here is K because it is pasted, copy-pasted from a paper, but K is Julia said. Not necessarily. Cannot be very bad. I will comment it in a moment. And the problem, there are several definitions of pressure, they all do the same, except on periodic orbits. Here is correct Julia said. Because it's a periodic orbit, so outside and
So in the real pressure definition, it does not need to be in the Julia set?
no, because if you have simplest case, basis of attraction, then you take any point except if it's super attractive orbit, and then three of preimages behaves even easier than if you take a point from the Julia set with which you need to be careful.
What is K?
No, it's J.
No,
J.
the definition tree pressure.
I say, I just explain.
Oh.
K, I took it from another paper where K was something more general. But read it just Julia said or something. No exception. As I say, it can be point in the basis of attraction except super attraction. I explain it here. And I think I need to give some explanation on the blackboard. Let me see maybe. Because I marked it in some places where I should give explanation of the blackboard, and here I didn't mark it. So also so if I have a point, one is here.
It's right here.
What? Here. Here, very nice. So I take a point, let's say X, and I assume something about this point. As I say, Julia said, but not necessarily Julia. And I take preimages. Etc. And I take a neighborhood given n. I take neighborhood of diameter x minus delta n. And delta arbitrary is equal to 0. Then I assume two things about this point. One, that it is hyperbolic, which means that I can go iterating f forward of epsilon times n, epsilon related to delta. I can go to large scale. And another, that it is safe. Safe means that fj critical points do not belong to this ball.
What is the relation between delta and epsilon?
There is some relation, it doesn't matter. Both are small. Because the relation is related with some exponent. So if the point is safe, then I assume safe not only for this ball but for 1000 billiard ball, because I need some reserve for the storage. So should be this extended ball. And then I can take preimages after time n. Not necessarily small, but there is some margin which stays when I go back. And then, this is time n, and then I can iterate backward sometimes. Actually, to do this, I should take safe not for time n, but for time 2n, in order to keep injectivity, able to write linear branches. And be back here, together with this color. So I start with a point here or here, let's say here, and go forward and finish here. Now, to discuss, to compare it with periodic pressure, I do shadow. So there is periodic trajectory here. Period will be not n, but will be n plus some constant. This time is constant, depending on the size of this big ball, plus this epsilon n. And
so this constant basically is such that this constant iterate of the ball covers all Julia sets, something like
yes, yes. But what I told was looking backwards. So, if you have this periodic trajectory from the Z, then F M prime F Z is less equal some forward, or you prefer backward. Let me write it forward, but I'm interested in going backward. forward is less equal than Fn prime x times some constant times Lipschitz constant in power constant plus epsilon n. So forward derivative periodic point is less equal than this up to some constant, which doesn't matter because I take 1 and log. So going backward, I obtain larger. That's why periodic pressure is larger or equal than K pressure. But I did it for special x. For special point x. This still pressure here. First question and main question is whether such x exists. But it exists because there are hyperbolic subsets which are non-trivial, not just individual and independent projectors. And they exist by construction, say, of maximal measure. Like you take a disk, take preimages, like here, but big disk, preimages, then some of them capture critical value, not too often, and most of them you need to remove some of the backward branches, and then most of them even not capture critical value, but they don't capture preimages which are too big, because too big there are few of them, no space for more. So most shrink as I want, so don't capture critical value, and more rare, and you build, and then you make the same or not the same. Yeah, you do the same and you build a hyperbolic set. Not just individual trajectory, but plenty of such trajectories. You build a horseshoe, one can say iterative functions. So it has non-zero entropy in particular, and therefore hyperbolic subsets. Maybe the way I explained it is too long, but I wanted just to find hyperbolic subset. It is, I have just constructed it. And this is construction by Manie, Freire, Lopez, and I think Lubitsch independently at the same time. I didn't read it precisely. Lubitsch. Manie, Freire, Lopez is easy to read. So this is to find hyperbolic point x, and quite many of them. Even in invariant, big hyperbolic invariant set, in the sense, big in the sense that it has even positive Hausdorff dimension. If it has positive.
This hyperbolic set is that which you construct by hand.
Yes. So Hausdorff dimension of this is bigger than 0. If it is bigger than 0, then almost all points in it must be safe. Because safe when image shrinks of critical point shrinks exponentially. This is where there is danger we capture such a point. It grows polynomial number of this disk when we iterate forward. Shrinks exponentially, number is polynomial. So it will cover infinitely many times 0 Hausdorff dimensions, by definition of Hausdorff dimension.
So the measure, you mean the Hausdorff measure or
Hausdorff dimension. how to know what is house of dimension, we need to look at the house of pressure, but with any exponent you have zeros and dimensions.
I mean, you said that for almost all points,
So for almost all points in X, all points in X are hyperbolic, but almost all except much smaller even than house of dimension are safe.
Not all?
A priori, maybe critical trajectory jumps very close to. Of course, it may happen that it jumps very close to points of, say, periodic trajectory. Why not? It's better to describe it combinatorially. Now another problem is, okay, we have such X, but it is a little bit unfair. Because we want almost all points are like this. Not almost all in the sense, are safe, but we can first prove the theorem for safe points, hyperbolic and safe. But this is maybe a thin concept. But we can take given Y, which is maybe not safe, we can take which is maybe not safe. No, we want Y safe, but maybe not hyperbolic. Safe, but maybe not hyperbolic. Then we can take X, which is safe and hyperbolic, about which we know already.
So y is another safe
Just
point.
N, another safe point. And we join them by a curve, which can be covered by disks. Number of these disks is less than square root of N up to a constant. This is a very useful theorem.
But omitting is constituent cell.
And twice bigger disks omit critical values. So the model situation is that we have such obstructions, these points of the critical trajectory, and we join two points which are within some distance from these points, which is sufficient if we take safe, also exponential y exponential minus delta n, and we can join them by a curve pass from here to here by using not n but only the square root of n disks.
what is n in this picture?
Just arbitrary. We take critical trajectory up to time n with some abstractions.
But how is it related to the grid you?
This is example. This is example to explain how square root of n appears. We have n obstructions. This is rather most hard configuration, and we can go from one side to another by square root of n.
So n is here in the requirement is such that fj of the critical points for j from 0 to n does not land inside this.
Inside is twice bigger.
I see.
Yeah, I should have written. These points are not in these u slightly bigger. These are u. And bigger disks are u. So when we want to compare preimages of this point to preimages of this point, we do along these disks. Number of disks is square root of n. Distortion is bounded by a constant, because we are safe by twice bigger this. So pressures will be the same. So that's how one can eliminate this assumption about hyperbolas. So I started doing these things in the 90s in my papers and transactions of AMS, and then some more ordered precise theorems in my papers with one Rivera, because these are basic technical things to be able to work with this triangle. But what I need to say, that though I explain it, so this proves also that this trivial property doesn't depend on point, except points which are too fast approximated by critical. Hyperbolicity, it doesn't matter. So except zero out of dimensions. Points too fast approximated. So we have an idea that the pressure is less equal to this. But opposite was mystery. So as I told you, opposite was proven first under some assumptions by being the Makarov and Smirnov.
So looking from your new result, the identity follows from for all rational maps now, or what is the...
This is mystery. I don't have tools.
So what the question was?
Whether equality holds for all rational functions.
And Makarov, Smirnov,
Makarov, Smirnov, and Binder proved it for polynomials, but not all polynomials, but assuming that all periodic trajectories are hyperbolic, rectangular. I will tell you in a moment what is the idea.
Which paper is it?
I will give you precise references at the end because I put this in Duke in 2000. History for me was that there was a conference in Brazil. Staff Smirnov was a student there, and I was also working on this, but I couldn't do anything. And I was very surprised that Smirnov can do something about equality. So this was really a very fundamental thing.
Okay, so this is the paper harmonic measure. This one?
It is on the last page written, but I have it written. It is in Duke, harmonic measure and polynomial geometry. This is only part of the paper. Paper is on other things also. So this P conical is my paper in transactions. these pressures. This is paper is one and starts in ergodic theory dynamical systems. Two, because the first one, our joint paper was in Invenciones 1 year before. And then in this paper, we managed to prove this equality in this PRS2 for all rational maps, but assuming something, which is hypothesis. Hypothesis H says again that it cannot happen that we have exponentially close bunch points periodic close period exponential random plane, which I already forwarded. So assuming this, we can prove.
And you now can prove it for
quadratic polynomials.
polynomials.
What should be possible? So certainty. It's what I was thinking about last days. If it is correct, then we can remove this score. It depends on the mean. Where is Cremer fixed? Oh, I lost it. I lost it. It should be the equality of pressures. Oh, no, it is just equality. Cremer periodic will be explained later. Here is the assumption by Binder, Makarov and Smirnov, which is stronger than I do. I assume that in exponentially shrinking neighborhood, there are not many points. They had stronger hypothesis that there exists R, that independently of what period it is, even in this fixed neighborhood, there are few fixed points or periodic points. But again, their proof works under this assumption, hyperbolic repelling. It does not mean uniform hyperbolic repelling from periodic orbits. Uniform would mean topological Collet-Ekman, and this is easier. Here I have a blackboard to remember to explain it. I will use blackboard. And as it is written, it's also used external arrays. Because they use it as polynomial. Use this tool and puzzle structure. And they ask the question I try to answer today of polynomials. So they have, let me draw. They use existence of repelling periodic Repelling points which are double accessible. Which is not hard to show that this is the case if all periodic orbits are repelling. So there are some points that you can start with to build puzzle structure. Otherwise, even you cannot even start. Then there is puzzle structure. These puzzle pieces.
By double accessible, at least double
At least two. And then they prove that if we have puzzle piece of generation, this is puzzle piece containing critical point. Now we can take preimages and have generation puzzle pieces. And they prove that if we have two critical puzzle pieces, then this distance tends to infinity. You cannot approach critical point often if size of generation of puzzle pieces is big. This corresponds to a very easy fact which I use since many years, that if you have a critical point, then every trajectory cannot, a trajectory cannot be close twice after short time. If it were, you would have contraction, because you have strong contraction due to criticality, then expansion controlled by Lipschitz number, and then if time is too short, then you fall inside. There is attracting to the problem. And nature of this fact is the same, but this needs to be proven. And they put proofs in the paper, sketch, but referring to Jan Kiwi. So it seems that it is Kiwi theorem, which they just for comfort of the reader repeat. I read it some time ago. The nature of this fact is clear. Having this to deduce something not about puzzle pieces but about disks, that you cannot hit too often this close to critical value is easy. It's easy corollary. And if it is so that time is long of two consecutive visits close to critical point, then it means when you take preimages, what you want to prove? You want to prove something about number of orbits going together. So if there are no critical points, you go backward, you don't get new periodic orbits. It's not possible. So some breeding of this number of these periodic orbits can happen only close to critical value. So there are some exponential methods. This idea. So this is also an easy piece, but harder is this. But not very hard. Okay, now I can move forward. fantastic. If I had 1 hour, I would become nervous. But I am at page 7.
Yeah.
But there are some blocks later which I can omit and show picture. So it will not be this. Okay. So it is.
I have one question regarding your definition. As you remember, by accident we discovered, reading your paper actually, that the lim sub can be replaced by actual limit in pressure. So for periodic pressure it's also, is it also the case?
Good question, but I would guess that yes.
Yes, I mean, because it is just a translation.
Yeah, but it's a good question. It could be added. If it is not already put somewhere, I don't know. I will try to. So here again is what I said about direction.
Wrong direction, yes.
I see.
Even
So something changed. Because I keep it upside down. That's explanation. So here is this three motors. Condition. Okay. For interval, it holds. Because you can, I will tell about this later, if you have a set where you go forward, you meet critical point from time to time, then you can split interval into sub-exponential many smaller intervals or domains in complex plane, so that in some of them you don't meet critical points going forward at all. And in such a good thing, you can further split to have even far distance from critical points. But the question is whether maybe still there is a bunch of periodic trajectories. If we have a domain in complex plane, it is clear we can have this, and then after a long time we can have this. Critical points are far. I will later formulate a theorem about this, but you don't know how many periodic orbits. The mapping can be very close to identity, and you need to use some miracle. But for interval, you have the following situation. It would be diagonal. And Fn. If we have critical points, like this, and then another critical point, then this is possible. But this corresponds to this. And you cannot have a situation like this. Of course, an assumption is needed.
So negative
That all periodic orbits are repellent. Or Schwarz and derivative is negative. Both these properties eliminate this. Of course, all periodic are repellent, which eliminates this possibility, or negative Schwarz and derivative also eliminates such phenomena. I think we mentioned this in our paper with Stas and Horn. So interval is easy. Not easy, but the one key point of the proof is not existing. Right direction. Okay, now some reminder about what is Cremer point. It's where absolute value of derivative for fixed point. For iteration, the same for iteration, has absolute value 1, but also approximation by rotation number related to this rationals is fast. More precisely, it is here. Here are people who worked with this at least long time ago. Now I don't know who's working with this. And if Qn escape fast, which means fast approximation, and there is a divergence, then we say there is Cremer fixed point, which means the mapping in the neighborhood of this point is not linearizable. So there is, as if Ziegel disk, which otherwise appears, is collapsed to a hedgehog. If additionally the escape is not too fast, then you have periodic orbits. I didn't analyze this last since 80s, so I don't remember the idea of this, but it is like approximation by rationals of rotation angle says that not at this point but nearby, this rationality geometrically is realized. So this is explanation of this. But if I didn't write this, but even if the approximation is faster, then the number is more Louis than this alpha, then these periodic orbits again, it happens, disappear, and they somehow are swallowed by Cremer. So here again I rewrote my main theorems. Here not only sub-exponential, but at most one of with each n. Period n. Probably not for all n. For most of n they don't exist at all, but it should be numbers qn where they have a chance to exist in Diophantine approximation. Not for the same. I haven't tried to do anything. And here for Cremer periodic, but for Cremer periodic, just one is to, I see no way to prove it. I hope to exist again without this number. Interesting thing is that I assume, having Cremer point, I assume that the whole trajectory is in such neighborhood of radius x minus delta I, but it is not needed. Sufficient is 1 point. Because for time not bigger than n, for iteration, distortion is very small. Even for iteration. So if the point is very close, and derivative is absolute value is 1 at Cremer point, then the size cannot grow. It can grow, but slowly. Here's explanation why there is only one critical point, why one for quadratic polynomial, of course. Why Julia set is connected, because this critical point must assume trajectory must assume the boundaries. Ziegel disk, so there is no critical point escaping to infinity, causing this connectedness. Here is one preprint point could serve several universes. And there is Shishikura paper, which I did reference, when the theory is elaborated. Okay, here I repeat the same. And here is the main idea of this story, that we have external arrays. And if we have external arrays, then the problem reduces to, more or less, reduces to study one-dimensional real dynamics. Some monotone, finite monotone subsets at infinity of external angles. It is not so much complex, because we have somehow parameterized by the circle of these variables. And here is Miller's theorem, to which I will refer, which is not very difficult, but it is the beginning of this paper. We have, I will maybe show you, let's read it and then I will show you pictures. So we have subsets of the circle, arguments of infinity. And here you have conditions, then they are finite. The map from aj to aj plus 1 is doubling map, circle. But there is a cyclic order in these angles, of course, because they are in the circle angles. So we discuss cyclic order geometrically. Geometrically, not dynamically, because and the condition must be here. And another important assumption about these sets. So, which are fundamental conditions? 2, preservation of cyclic order between aj and aj plus 1, and unlimited problem. I will show you a picture. Here is from Miller. So here is first, here is a fixed point, so called alpha fixed point. There is W period bifurcation, and after W period bifurcation, we are ready to make consecutive bifurcation of rabbit type. So altogether, these external arrays are a number 6. And you can look at the angles and study each step angle grows by 2, except at some point where we are somewhere here, a critical point, and then the angle of the image becomes more than 2 pi. Actually, and here is, I will show you a more schematic picture. So this is the type of picture of the surface, minimum surface. So this is formal portrait. You see unlinkage, because we have edges which end here, edges which end here, orbitals of period 2, and there is the game of bifurcation to period 6, which is here marked by these external rays. And the mapping is injected from this to this and from this to this. but at some point there is a critical point. So this image, monotone, and some tradition. And there is critical value here, 0 is critical point. And critical value is in the smallest sector. This is your not very difficult. So we have situation critical values in the smallest sector, then we have images, the sector grows until it is big, capturing critical point. And the next image is even bigger, but it has self-intersections. But rays are close to each other because the image after 6 times, it's not from here to here, but from here to here. So we don't have time to analyze this, but I spent some time to understand. Of course, this critical point works twice here because I have somehow from this and this again using already critical point, and then next time. So appearance of critical point appears at each step. So there is a lemma which I use. This is my key lemma. But if we have such a situation, then we have two cases. Either here should be small scale. Either valid, how to say this graph, many edges in one vertex, how we call this number?
Degree of vertex? Degree of a vertex? Or?
Yeah, so number of V is number of edges ending at one point, validity. R can be the same. R is number of orbits. No.
What is R in the previous picture?
R is here.
R is what?
No, valid. R, yeah, this is R. Is you have 3 edges here.
Yes.
Now the question is how many orbits are over one point? And number of orbits might be smaller. So each of these things can belong to a different orbit. But this is not the case. The case is either that this is just one orbit, so this is transitive. So we go here, 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 and we use all of them, or at most 2. At most 2 happens, and it is called primitive case. If we have a primitive bifurcation, so we have kind of this. Let me say this is period 3 phenomenon in the real life. So we have this has no, sorry, I wrote Mandelbrot in place of Julia. Nevertheless, let it be Julia. Here is some this, and here, except it is period 1, here is some Julia. So we have 2 sectors. And then this goes to itself and this goes to itself. There is no transitivity. This goes towards something here, here, and it goes to something here. So So if the case is not primitive, then we have transitivity. If it is, then so this goes back to this, and this goes back to this. No transitivity. That's why you not discuss notation here, which is 3. Doesn't work. Oh, so don't read it because it is unpleasant to read. We have either transitivity or we have two orbits. But if I have some idea that I realize that if we don't consider graphs like before, that we have several edges ending at one point and several edges ending at another point, but there are little gaps between these vertices, allowing a priori rays go through these little gaps. This is my situation. My rays don't end at zero point. They end slightly close. There are some gaps there. So a priori could be, but this thing, if I know the conditions, I mean, that there is unlinkage, that order is preserved, then I can ignore these gaps. Rays cannot go through gaps between edges ending close to another Cremer point. This is the main idea. So in the proofs I take the same graph, and then I try to prove minus conditions. Unlinkage and order preserved.
The graph you showed corresponds rather to landing rays, yes, so not Cremer points. This is
Yes, that's a problem. That's a problem.
Yes.
But the situation occurs to be like in mirror, as if they all finish at one place, one vertex. On my picture, two vertices. In fact, here I don't have this, but they end close to this point. And I need to prove that when I take image of this does not sneak somehow through this point, changing the sector. And also I need to prove preservation of the order. For this case, it is trivial. You cannot change the order. There is no possibility. So this I told you already. This is what I told you. We need to auxiliarily know that in time n there is no escape or deformation of the impedance. But this is easy. I don't need to make computations because the derivative is 1. So the value of derivative is 1. So if I have such small bits, then it is. Suppose we have exponential. Suppose we have repelling, but very slow repelling. If we have very slow repelling, then if we are very close, we cannot overcome this slowness. Ludwig knows this because he used such things, I think. Because parabolic phenomenon dominates, at least at the beginning. No, for most of this time. So even if you don't have neutral behavior, but repelling, but slow, then you cannot escape in time n from such label. So here the situation is much better. That's why I even edit this r. This is already exponential like this, and multiplied by this, which is slow exponential.
What Does R not? Is it fixed?
R is, no, R is, yeah, it's not well written. I should have this because this makes trumpets. So this is a preparing for this. Was not. I got lost because I thought it is a constant. So would it make sense? This is growing. But it's misleading. I need to correct. And corollary is that if I know that the disk doesn't grow exponentially, very slowly, then I can estimate distortion. Then you have product which is exponentially approaching 1. So it is even better, even for iteration. G. Because I take this is. Maybe I wrote it for so I have distortion control for iteration.
So here G is iterative term.
I don't know what. This is the, yeah, because later I use G as iteration of F in our P, where P is bigger. So it's a little interesting. Now will be the most interesting part. Because I remember. So because I will use Green's function of the base. Phi is Riemann. So Riemann, I want harmonic function in Green's, I take it. Now, let's consider capital K periodic. And I will try to prove that K is at most 2 or 1. I will refer, checking Milnor's conditions, I will refer to this theory. First, you need to know what is number of external rays landing at repelling periodic orbit or point. But it is fine, it is not difficult. And mapping is monotone. So here, if all these rays end at 12, then we easily have monotonicity. Because monotonicity is in the small neighborhood of this point, and then we have external rays which cannot enter sectors between other two rays because there is no gap. So in this case, Miller gives more arguments. I also wrote it more carefully because you need to have critical point far from this to control anything. But it is. But I want to prove something much harder.
So I'm sorry,
Yeah,
so we are talking about external
we are
rays
talking about
landing at
landing at periodic trajectories close to Cremer.
at periodic
Close to Cremer. Because this is the case Cremer fixed section Cremer fixed.
Okay.
To my surprise, these things appear very
So
small.
you so any other periodic point is
No,
not
I am
Cremer.
interested only in periodic point.
Yes, but they are not Cremer because there is only one. So
Yeah, but okay.
and they
Do you know any external array ending at Cremer? I don't think. maybe it is strange. Yeah.
And I just wanted to understand.
No. I'm interested in this repayment.
There's a quadratic
Quadratic polynomial. So it is a little bit difficult to work just. Here, okay, here, fundamental. Good. If I shall prove preservation here in this Milnor scheme portrait, I have only one vertex and all rays and close to one point, the Cremer point. I will have something more like in Milnor portrait if I have periodic order. So this is easier. So I have just one, say, neighborhood of this Cremer point, and all rays I'm interested in, and inside. So I have one vertex and many edges. Before I explained that the mapping preserves order for each periodic point to its image, or for iteration to itself. But here I will prove more. There were no gaps, but I will prove more. I will prove that the cyclic order is preserved for all external rays appearing there. These are the union over X on the periodic order, not individual for each X. Each X can have several external rays, but here I want union. Here are some, we have time to discuss, because we have extension of such sectors of this. We can close complex plane either by a point or by a circle. Better by a circle, because then I have external rays. So what I do, I take rays which are slightly shorter, in the sense infinity is infinity, you cannot make a ray shorter.
But could you make a picture?
Yeah, and they will be several. But I just want to say what I want to achieve. Maybe I will make a picture here. Yeah.
Z0, which is Cremer point.
It's indeed a good idea. Good idea to make
Just if you could draw this external rays.
So this is Cremer,
Yes.
and they all start here.
And these are those periodic points which are close to.
Yes, some will be two.
Yes, okay.
I will prove later, maybe I will not have enough time, that in fact validity here is at most two. This is a nice and easy proposition. But it doesn't matter. So we had our external rays, then we make a trick. Here, subrays. Instead of ray, parameters, instead of ray, we shall consider only part of this ray, starting from the last time of where the rays leave, last or first, depends, where the ray leaves this disk. We are not interested in this part of the ray. So these things before can mix somehow between these points, can go through. But I'm interested only in this. it is not enough. I want, studying preservation of the order, cyclic order, I need that these rays, images, the images don't enter a little bit here. See, images, I will wait later. So I need to make them slightly shorter. So having an orbit of this, of one ray, I take the one where Green's function is biggest. Which means, because Green's function under iteration grows by log 2, then if it was the biggest, the image has even bigger. The whole ray is in the area of Green's function. So So I do such telescopic construction. I take an array, its image, and then its image, etc., until the period, and then we don't land at the same, but at something short. But each time we land at something shorter than the original. So in other words, I started with the widest channel, with biggest Green's function. When I take images with a larger and bigger channel. So we are also. So we do by this way we obtain forward invariance of this family of rays. So the property I obtain is like this, that after taking this new family, such new ray starts outside, but close, because we have nth iteration, and it is close to identity. And I obtain something like this. Close, but everything is okay. So these are my improved rays. And this is what was written in the previous slide. It is written here. Conclusion and begin of the ray is in this ray. Here is definitions. Here is smaller is my improvement, but I can still take smaller array, shorter array, starting from not R but from 2R. It is technical. So I have here even something better because I take the last year twice. Now I consider sectors. We have here sectors, Q, Q I extend back to the place it the sector myself. I have sector Q2. It is between rays and piece of the circle.
The original race.
The original, I need, at this point, I don't feel it. I just draw it. Here, I take image of a sector, but I join all sectors to one big sector which I call regular. There is one sector which contains critical point. I don't like it, but I consider together all regular sectors. one big regular set. This was an idea for me fundamental. If I didn't consider a critical point,
So which
then it was hopeless.
so which set takes close regular? The one
Union. This is, I will give you this one. It's union of regular. So, here is definition. This union, no, definition is that it is gamma, so let me not read this.
oh the union for
If we have one sector where it's critical point, I think union of another.
Okay.
The polynomial. And here is my image of regular sector. I want it to be like this, because inside the regular sector, order is preserved on these rays. Because it is just Jordan, but the problem is why the last ray of the image of regular sector don't jump over the first image. And what may happen? I want to achieve it by proving that image of this ray, so this was image of this ray, but I extended it by the original. And here the same image, but I extended it on this page. And the question is why this cannot cheat and go like this, may changing the order. It cannot, because it cannot enter through this curve. It must go down because it is outside this. There was forward invariance of this x. This must go like this, but it cannot because it is outside this. So it cannot enter directly to this, but there is a sub here through or tube through which it must go. So this is again an idea, an important idea. So this is one impossible case. And another impossible case is, I don't have time, so I will show this. It is why it cannot come from this side. So we have, because I want to prove that this thing, image, does not have set intersections. This is sufficient. But on this picture it has set intersections. This cannot intersect this, but can be very close to this. So I prove that this is not possible. Because we can have, my time is going to finish, so I will explain quickly without showing slides. Because if this happens, that we have such thing to our map it to this, then, and if there is self-intersection, then we can slightly extend this domain by adding something, adding image here. And then there we avoid self-intersections. Why we can extend? Because when we extend, we lift. When we lift, we are in this suck. We don't capture critical point. This is elsewhere. So in fact, I slightly extended, remember, avoiding self-intersection. And then after some more arguments, if this image has no self-intersection, then infinity has degree, it doesn't go more than 2 pi. It cannot go around. But my time is almost finished, so I will show you this. So these are phenomena which I avoid by these both considerations. Here you have kind of local injectivity. Image intersects. So the first argument excludes this, it's excluded this. I need to omit this. Here's proposition I promised you to you, that in fact validate this proposition. And here is periodic. I remove everything except picture. In correction of this, would be that all three should be the same size. These are these disks of radius r. So the problem is that if I start close to this of radius r, I could separate two rays starting here. I told you the size of this and this should be the same. I would separate, but I cannot separate because otherwise, if I separate, I go to this, which is not possible. So I must go back. And this is a key argument for unlimiting. Even with the space here to separate is big, then at the end is not. And here is what I told you, if we have even plenty of points, then we can shrink number of points and critical point is 4. And here is the main proof of this, but I will show you this on the picture. This will be very because it is easy to show on the picture. What I do, I take such a disk. X is not periodic. We forget about Cremer because this is Cremer. I never used Cremer. Just to know there is a bunch of parts going close. I didn't use it. So here I forget about Cremer, and I have a disk and images. Maybe not intersecting. These are slightly bigger images than my. These are slightly smaller disks than my radius R disk. So they may intersect. If they intersect, the mapping due to distortion control are almost translations. Not translations, but similarities, but I can modify the differential that it is one and Cremer. Or just take the point who is biggest size. So the differentials for images are less equal to 1. At the end it is 1 because it is periodic. So, and then I take all this family. It was of the same. What size it is? That's something else. I take some neighborhood and do the same. Etc. What I do? I consider the shortest time we come back. We have this picture. I consider the shortest time it comes back. If the shortest time is just period, it is just what is just period, then it is done. It means we never come close. If we never come close, then we have picture like several disks in the orbit, like periodic Cremer. But if we are each time we are close and never get large modulus between this family, then it is like fixed Cremer. But how many this operation happen? How many times this operation happens? Each time, if we have these times kj, we have next time not bigger than twice smaller. So number of times we do this operation in case we don't obtain separation is logarithm of n. And then, no, if it is logarithm, then it is constant. Size of all this family, if I never get this big modulus, is constant in the power logarithm of n. So it is small. So we have situation like Cremer fix. That's all. Thank you. Oh, I promise it you. Here are some positions.
Okay, let's any questions, comments? So I wonder, do you think it is likely it's possible to extend to all polynomials, not just quadratic ones?
So, because there are several critical points. The Milward paper is about quadratic. Of course, really critical is this. And then this was 20 years ago. So I am almost sure, and there are some generalization of this field. With many critical points, it becomes
Makarov and Smirnov.
No, they do for all polynomials.
Assuming hyperbolicity.
But they assume which allows to construct others. You don't even know that there is one point which is double. I don't know, again, I analyze I kind of newcomer. And from rational, no proofs. Thank you. More questions?
Just questions, comments? So, questions, comments, thank you.
Happy Easter. In 2 weeks, it's possible that we have 2 talks. Grammar and Zorowicz and Mirek from Wrocław. Mario. But it is not